Hello, today we are going to be looking into topic 3.18, the tangent function. Everything we've studied up to this point has been really the sine and cosine function, really making sure that you knew all of the ins and outs, understood where the values on the unit circle come from, as well as how that transitions to a rectangular type graph where you have angles on the horizontal axis and distance, the radius on the vertical axis. But as we spoke in the very beginning, remember that there are actually six trig functions in total. We have sine and cosine, which we use a lot, maybe the most. Then we have tangent, which we're going to begin our in-depth study today with. And then we also have secant, cosecant, and cotangent, which we will pick up at a later date and go a little bit more in depth on those topics as well. So let's start by recalling that when we first introduced the idea of the tangent, of an angle. That was back in topic 3.2. So if you need to refer back to the first reference to that, you can definitely do that. You should have those notes. And we define the tangent of an angle as the slope of the terminal ray. All right, so it's the slope of the terminal ray, or as the ratio of the angle's sine to its cosine, because we know that slope is vertical over horizontal, y over x. We know that sine is our y, cosine is our x, so we have lots of connections there. So these are all rules, if you will, that we've talked about. So we know that it is sine over cosine because this is y over x. And then that's another way of saying we can use the m symbol because remember we learned that in Algebra 1, slope is also referenced as a symbol m. And then once again, back to the theta, which is y over x. And then all of this is pertaining to the ray of the terminal angle. So just kind of recapping. So on your paper, you have a circle like this, and we're going to use that for a couple of explorations here to make sure we understand the behavior. So what I would like for you to do is draw your markers for your vertical and your horizontal axis. So you're going to have one that goes down the middle this way and one that goes down the middle this way. So we have that origin point right there in the center of our circle. And go ahead and label the quadrantal angles. So we know over here we're at 0 or 2 pi, and the coordinate point here is 1, 0. And if we're up here a quarter of the way around the circle, that we're at pi over 2. And we know the coordinate of this point where the terminal ray intersects the circle is at 0, positive 1. And then if we're going to this edge of the circle here where the terminal ray would start at the positive axis and end here, we know that that's pi and the coordinate is negative 1, 0. And if we go 3/4 around the circle, so we're down here when we're looking at this point, this is 3 pi over 2. And the coordinate of this time would be 0, negative 1. And so those quadrantal angles we learned way back, and we looked and studied the fact that this was our cosine and this was our sine. So in these particular points, remember it's still cosine sine. So I think I'm going to take this one and label it just so we have it in our notes, cosine sine. So it's that horizontal displacement, which is the cosine value, and the vertical displacement, which is the sine value. And the tangent then will be this ray that's at the end, the terminal side of the angle. So as we did previously with sine and cosine, we used our understanding, we're going to use our understanding of the tangent function that we began talking about in 3.2 to develop the graph. And we're going to use then look at the slopes of the terminal rays of our angle as we do that. So the first thing I want to look at is if we start thinking about angles increasing and we're going from 0 up here to pi. Okay, so we're talking about that direction, positive direction. So just thinking about the angles that we've looked at so far. So we had 3 spots within this quadrant of angles that we have addressed on our unit circle. So I'm thinking about the terminal side going to this point, which would be the angle pi over 6. And then I want to think about the terminal side going from 0 to this point, which would be pi over 4. And then I want to think about the terminal angle that's going from this side up to that point, which would be pi over 6. So as we're looking at those terminal sides, the tangent is the radius of the terminal side. So what is happening here? If we start looking at the ratio or the slope of the side, we know that we have our coordinate points from our unit circle. So what I mean by that is I'm going to turn this sideways just a little bit so I can write straight here for a sec. And I'm going to do square root of 2 over 2, square root of 2 over 2. That's that coordinate point. Okay? So write those coordinate points down for just a minute. Stop your video, get those situated. All right, so as we look at this, so remember we're going on this yellow arrow arc of the circle up to pi over 2. We have our coordinate points here. So what do we know? As we know the value here at this point, we know that that is 0, right? If I look at this terminal ray that starts and stops at the same point, then if I take sine over cosine, which because that is the vertical displacement over the horizontal displacement or the slope, then I'm going to be looking at 0 over 1, which is just 0. If I'm up here at pi over 2, it's been a while since we talked about this, but if you wanted to approximate this, if you were to physically take, you can punch this in your calculator, use the pi symbol, divide by 2, then you're going to find that's approximately about 1.57. Okay? We did approximate in our first activity the distance of 1 radian in terms of degrees so that you would just have some mental reference. But what I'm talking about here is the terminal side of pi over 2. And so I know that that is where it ends on this quadrantal axis. I know that its value in radians is pi over 2, and I know that if I take pi and divide it by 2, it's approximately 1.57. Okay? So what about if I go halfway around the circle to pi? What is that approximation? You guys know what pi is, right? It's 3.14. Okay, so we have that approximation. If we go all the way down here, so we go from 1.57 around to here, then we should be able to determine that approximation as well. And that is about 4.71. And then when we get all the way around the circle, which is more than 6 radians, right, then we know that this is also, once we get all the way around this approximation, it's roughly what, 6.28. So it's always a good idea in your mind to be able to kind of approximate. So all values that start here and terminate here are going to fall between 0 and 1.57. Okay, so that means as I look at this ray that's going from the origin to this point, and then the next terminal ray that goes from the origin to this point, and the next terminal ray that goes to origin from this point to this point, what should be true about those values? What's happening to the length of that ratio, the length of that radius? All right, can you see that it should be gradually getting bigger? There's an infinite number of rays that can happen in here. But if this starts out at 0 and it approximates all the way up to 1.57, then these distances of each of these rays should be getting gradually larger until it gets close or approximates 1.57. So how could we actually go about that, finding the tangent value? We know that inside we have root 3 over 2, comma 1/2, which is cosine sine. And what is the ratio of tangent? Sine to cosine. So if I wanted to calculate the tangent value at this point, then I would take my cosine value, which is 1/2, and I would divide that by my cosine value, which is, according to this, root 3 over 2. And if I'm going to divide by a fraction, then remember that's the same thing as multiplying by its reciprocal. So what is that going to look like? It's going to look like 1 over square root of 3, because those would cancel, which is a good approximation. However, as we started learning our unit circle, remember that we said all of the unit circle values are rationalized. So if I want to rationalize the tangent value here, then that means I would, let's see, I can squeak it in right over here on the side. I can multiply by root 3. I can multiply by root 3. So this value then is 1 times root 3, or root 3 over, and root 3 times root 3, since they're both square roots, we can multiply the radicals underneath. So 3 times 3 is 9. What's the square root of 9? Which is going to be 3. So there are a couple of benefits to know. One, in case you're working a problem that may not necessarily need to be converted to a unit circle kind of value, that 1 over root 3 could be the tangent at pi over 6, or root 3 over 3 could be the tangent at pi over 6. So now we know cosine, sine, and tangent at pi over 6. All right, so we're going to build the rest of this quadrant here. So I want you to pause your video and calculate what is your tangent value at pi over 4. That one should be an easy one because remember the coordinates are all the same. And what is your tangent value at pi over 6? So pause your video and make those two calculations so that we can fill in what our tangent value is here and what our tangent value is there. Pause your video. Okay, so let's talk about what we found. So I zoomed in just a little bit on my circle so that you could see just a little bit better. But if we start down here at pi, then when we're finding tangent down here, then we would take the sine, which is 0, over the cosine, which is 1, and we said that was 0, approximately 6.28, if you went all the way around the circle one time. All right, so then if I move to my tangent value here, I did 1/2 divided by root 3 over 2, so we're multiplying it, and we talked about how to rationalize that, and we got this amount, root 3 over 3. So we know that if we're looking at root 3, we learned a little bit ago when we were talking about that root 3 would have to fall between radical 1, which is a perfect square, and radical 4, which is a perfect square. So that's going to fall in between, and we said last time it's actually 1.732. And so then by the 3 on the bottom, that means take a third of it. So a third of it puts us at approximately a tangent length of 0.577. So this is the value that we need to know. This is the equivalent for tangent. And so we're going to make sure we're identifying this value here so we don't forget about that. And then when we move on to pi over 4, well, we know the coordinates for pi over 4 are root 2 over 2, root 2 over 2. So in essence, you're taking something divided by itself, which gives you a value of 1. So can you see how when we approximated this at approximately 0.577, now that length is approaching or is 1. So then let's look at what happens at pi over 6. So at pi over 6, then we're going to take root 3 over 2 divided by 1/2. So when we divide by a fraction, we multiply by the reciprocal. Our 2's are going to cancel, and we're to a tangent value now of root 3. And that tangent value of root 3 we talked about a moment ago is approximately 1.73. So you can see we started at a 0.577, and as we got a little bit bigger, we were managing to come up with one that was actually 1, and then we got a little bit bigger, and now we are coming up to an approximation on this one that's going to be, I didn't write it down, 1.73. And remember that approximation is for tangent, okay? So as we can see, the tangent values are getting bigger. Then what happens when we get up here to pi over 2? So at pi over 2, remember it's sine over cosine. So then if I take sine over cosine, hopefully you saw that that's not possible. We can't divide 0. So anytime the tangent function as at pi over 2, we're looking at a vertical line. And what do we know about the slope of a vertical line? We know that it's undefined. Okay, so we don't have a slope at tangent. So that's what makes tangent functions, and in fact, all the other trig functions, a little more interesting, because since they're going to be a result of looking at a division or a ratio, then sometimes that denominator could try to approach 0. And we know when it approaches 0, tries to become 0, it's undefined. And we also know that that corresponds already to what we know about this vertical line, because we know any vertical line has an undefined slope. In other words, if I'm running across the room, I can't just start running up this wall without any suction cups or being Spider-Man or something like that. So anything that's a vertical line is undefined. So while we look at and could look at any angle in this first quadrant, so let's identify our quadrants. So I have quadrant 1. As the tangent values get bigger, as that terminal side gets bigger and moves closer and closer to pi over 2, those tangent values are getting bigger until they reach pi over 2, and then in which case it becomes undefined. So that gives you an idea of the behaviors of tangent in the first function. So let's proceed around and look at what happens in the next part of our quadrant. So we're going to say quadrant 2. So I'm going to put that over here somewhere so we have that marked. And quadrant 2, remember, goes from the vertical line of pi over 2 to the horizontal line of pi. And as we have talked about our unit circle in any of the quadrants, then we know we have kind of 3 points we're looking at. And so I've got a point here, I've got a point here, and I've got a point here. And as again, we're looking at the radius, so we're talking about going from the center to the point on the circle. So I'm going to take my handy dandy little ruler here and we're going to connect that up. And remember, we're talking about the tangent value, so that ray. And then we would be talking about this one. And then the third one in this quadrant we're looking at and analyzing the behaviors as they move from pi over 2 down here to pi. So we're talking about moving around from here to here. And so we're still moving in a counterclockwise direction. So we're talking about this piece of the circle and that ray right there. All right, so now we should be able to identify the angles. So at this angle, we're at 2 pi over 3. And at this angle, we're at 3 pi over 4. And then when we're at this angle, remember starting the positive x-axis and terminating here, so this is the terminal side, then we're at, how would we count that? What would that look like? Hopefully you got that when we come, so it'd be 5 pi over 6. So that's the 3 angles that we're looking at. So we're starting at pi over 2, which is undefined, and then our values are going to start creating as we go down here. So we want to know what's the tangent for 2 pi over 3, what's the tangent for 3 pi over 4, and what's the tangent for 5 pi over 6. So as I'm going to zoom back out here for just a minute, guys. Go back down to our document here. So let's kind of catch up in terms of what we've been talking about. So when theta is 0, the slope of the terminal ray is 0, right? So right here, that term above. So when it's 0, the terminal ray has a slope of 0. And then as the thetas increase, as we move this way around in the first quadrant right here, the slopes also increase. So we discovered that a moment ago. And then when we get to pi over 2, the slopes are getting steeper and steeper and more positive, right? So steeper, positive, and then we get to theta at pi over 2, and we have a little bit of problem, right? Because we said when we are doing this ratio of sine to cosine, anytime that cosine value would be 0, it's going to make it an impossible calculation to make. So when theta reaches pi over 2, the terminal ray is now vertical, and the slope of a vertical line is undefined. Now let's make sure that one sticks out here. So I'm going to say undefined. All right, so we discovered that a moment ago. So we can now say that the slope is undefined because it's an undefined line. And so if you are looking at saying the slope is undefined, we can tie this back to our limit notation. So the limit as theta approaches positive over 2, excuse me, from the negative direction. So we're starting here, we're working our way around here, we're going to go around here, and we're getting up to this point, then we can see that the values, the radius values going this way are going to be approaching infinity. So we can go this way, we can go this way. And that's just tying it back and thinking through what's happening in our limit notation that we studied earlier in the year. All right, now let's investigate what's happening in this new quadrant. We were just talking about going from pi over 2 to pi. And we're going to use that circle above again, just like we said. And we're going to look at the slopes from pi over 2 to pi, and we'll go ahead and look at quadrantal angles since those are the ones we're most familiar with, not quadrantal angles, excuse me, angles in quadrant 2 that we're most familiar with. All right, so just like before, let's think about what would the coordinate be, and if you need to write them down, feel free to do so. But we know that this is the result of reflecting this angle over here. So when you're looking at reflection from quadrant to quadrant, angle to angle, all of those things that allow you to, if you have this quadrant memorized, apply them to the other quadrants. So if this is 1/2 root 3 over 2, then everything in this quadrant, remember when you graph it, is negative, then positive, because we have that horizontal displacement in the negative direction, and then the vertical displacement to get up to the point on the circle. Everything over here is positive, positive. All right, so we know then if we reflect this point across the y-axis, it puts it right here. And my coordinate points now for this point are negative root 2, excuse me, negative 1/2, comma, root 3 over 2. So let me see, I'm going to turn sideways for just a minute and write our angles down. So if we're reflecting over here, then we know this is now negative 1/2, comma, root 3 over 2. We know that 3 pi over 4 is a multiple of pi over 4. So we know the coordinates are root 2 over 2, root 2 over 2, and the first one's going to be negative. And then if we look at 5 pi over 6, so it's going to take this point and reflect it across this way. And so now my coordinates should be negative root 3 over 2, 1/2. Right? So did you see how that wasn't about memorizing? It was very quickly just reflecting them over into that quadrant so that we knew how to get them quickly. The idea is we use them enough that most of them become to the point where when we say, what's the tangent of this, or what's the sine of this, or what's the cosine of that, you're going to have used them enough that they have slowly shifted into your working memory, even if you didn't realize that was happening. Okay, so now I want you to pause your video for a minute and I want you to think about what's going on here. I want you to calculate these tangent values for me, which remember using our tangent ratio of sine to cosine. We have the coordinates right here, and I want you to look what's happening to the lengths of these terminal sides. So when I say the terminal side here, remember I'm talking about from here all the way to that line, and from here all the way to that line, and from here all the way to that line. And these tangent values, remember, are the radius or the length of that terminal side, the ratio on the terminal side. So go ahead and pause your video and make those 3 calculations for me, please. So hopefully, as we went around the circle, we found that at 2 pi over 3, the tangent is negative root 3, and then it was negative 1, and then it was negative root 3 over 3. So all of these points were reflections from the first quadrant. So look at what our tangent value was here. It was negative root 3. When we reflected into quadrant 2, then one of our coordinates, the first coordinate specifically, the cosine value is negative. So then you're going to have a negative divided by a positive, which should always be a negative. So I can see that I can just reflect the value that I already know from the first quadrant to its angle in the second quadrant, which was 2 pi over 3, and that's negative root 3. So if this was 1 in the first quadrant, when I reflect it over here, then it's going to be negative 1 in the second quadrant, again, because we're going to have this division. One of them is negative and one of them is positive. And finally, the 5 pi over 6 angle, so that's coming from root 3 over 3 over here to negative root 3 over 3, because the cosine value is negative and the sine value is positive. So as we're thinking about this, then we're talking about these rays are all negatives, 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 and then it moves all the way around to pi. And when we calculate pi, look what happens. We're going from sine over cosine, so I'm back to 0. So I'm going from negative slopes, and remember we have approximations over here. So we know this one is starting up here, so it's actually approximately negative 1.73, and then negative 1, and then negative 0.577. So we can see as those values are moving in the negative direction, those numbers are getting smaller, and then they're actually approaching a tangent value of 0. Notice here it was undefined. Why was it undefined? Because you were trying to divide 0 by something. Or you're trying to divide 1 divided by 0. But now over here, I am taking 0 divided by negative 1, so I get a 0. So as these rays increase in length, as we're going around the second quadrant of the circle, then we can see that those slopes are moving closer and closer toward 0. So that's kind of the behavior in the second quadrant. So now we're going to move to the third quadrant. So we're going to have the third quadrant over here. It's kind of hard to read. Let's do this. One. All right. So we're in that third quadrant. And so what do we know in general about any point that is graphed within the third quadrant? We know that when we look at those points, it's going to be a negative displacement for the cosine value and then also a negative displacement vertically to get to the point on the circle. So all the points in this quadrant are negative, negative. So again, we're going to reflect some points around. So one here, and then 3 points in each quadrant that make up our unit circle. So we're going to have these quadrants. I'm going to take my handy dandy ruler here and connect the rays for the terminal side so we can visualize what's going on. Okay, so for this quadrant then, remember we're moving from pi, continuing in the positive direction, around to 3 pi over 2. So we're looking at how these links of these rays, this terminal side, and that the fact that we have tangent for each of those. Okay, so let's get the angles in here first. So we should know from our unit circle knowledge that if I take this and I reflect it here, then that's going to be 7 pi over 6. And if I take the 3 pi over 4 and reflect it down here, that's going to be 5 pi over 4. And if I take this point and I reflect it down here, then that's going to be 4 pi over 3. These are all prior knowledge things that you should know. You ought to be able to give me the coordinate for each of these places, right? So in this quadrant, it's going to be negative root 3 over 2 and negative 1/2. This one is going to be negative root 2 over 2 and negative root 2 over 2. And then this one is going to be negative 1/2 and then negative root 3 over 2. All right. So as we did in quadrant 1 and 2, I want you to go ahead and pause your video and I want you to use your ratio to figure out what the tangents are for each of these 3 points. Use what you know about reflection. Use what you know about how the points change. We have calculated tangent in a lot of places. Use your knowledge of that. So you have a lot of things that can help you calculate what the tangent value should be at these 3 spots and at 3 pi over 2. All right, so go ahead and pause your video and make those calculations and we'll come back and talk about it. Pause it now. So as we are looking at our paper down here, let's catch up just a little bit. So we've looked at from pi over 2 to pi, and we said that we can see the slopes are transitioning from negative to positive. So going from 0 and negative, 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 infinitely, I should be able to put any line between 2 that I have. So technically, I'm going on for an infinite number of times, an infinite number of infinities, I guess, negative numbers to get to negative infinity, until it tangent transitions to 0, because at this point, it's a nice pretty number of negative 1, 0, 1 unit this way, stay put 0. So 0 divided by negative 1 becomes 0. So now we're looking in the third quadrant. And so as we continue around the circle from pi to 3 pi over 2, we're going to look at the slopes and see what's happening now. Okay, so the slope of that line, which is the tangent value, then remember. And here's the one I will point out. Some of you missed on your unit circles. You did not reflect the coordinates correctly going here to here. You tried to make this angle. So just be sure you're being attentive to those coordinates so you get things right. So I can also see that if anything here, either of these quadrants, both of them are negative, so any values or points in this quadrant, any angle, I'm going to be doing sine over cosine, which just means a negative divided by negative is a positive. So my tangent values will always be positive in this quadrant. So if I reflect this, I reflected the coordinates, which means I would be doing negative 1/2 divided by negative root 3 over 2, which we already know from quadrant 1 and 2 is root 3 over 3, and because it's positive in this quadrant, my tangent value stays positive. All right, we know that the coordinates for any multiple of pi over 4 are the same, root 2 over 2, root 2 over 2. The only difference is the direction, and in this case, it's negative direction horizontally, negative direction vertically. Anything divided by itself is 1, and in this quadrant, it would be a positive 1. And then if I take negative root 3 over 2 divided by negative 1/2, we know that when we did it up in this quadrant and it was a negative and a positive displacement, that it was negative root 3. So down here, if it's two negative displacements, then it's just going to be positive root 3. So I should not need to be calculating this at this point. I should be able to take what I know about my unit circle and reflect that tangent value into the proper coordinate and know if it's negative or positive depending on what kind of displacements horizontally and vertically that you have. So then as I'm doing these and moving around this direction of my unit circle and I hit this bottom point, which is 3 pi over 2, look what's happening again. Now I have sine divided by cosine. Once again, cosine is 0. Once again, it means my tangent is undefined. And once again, we're talking about a vertical line, and we know that the slope of vertical lines is undefined. So it shouldn't be a hard time. This is just one big long vertical line. So anything that lines up with multiples of pi over 2 or 3 pi over 2 are all going to be stopping and terminating on that vertical line. And they're all going to stop and terminate on a vertical line, which we know does not have a slope. It's undefined. All right. So then in this case, when you're going from down here, sorry, pi to 3 pi over 2, we can see that the slopes are now positive again, and they progress from a slope of 0 when theta is pi to the slopes increasing without bound as theta approaches pi over 2. So the slopes approach positive infinity because there's an infinite number that can happen as I'm moving this way and we get closer and closer and closer. All right, so then let's look at the fourth quadrant. So what is happening from when theta is pi over 3 to getting back to the original part of the graph? So what is happening in those situations? So that means we're going to be looking in quadrant 4 and starting here at 3 pi over 2 and moving around here to pi over 2. And remember, we're opening in the positive direction. So we're talking about moving in this direction until we get back to where we started from. So once again, we're going to use our three main angles that are in this area. So we'll have, let's see, here, here, up here. So those are our three quadrantal points. And we know that anytime we graph on a regular coordinate system and we're graphing in the fourth quadrant, that it's always going to be positive and then negative. So we're going to have a horizontal displacement that's positive, but we're going to have a negative displacement vertically as you move down to this point on your unit circle. All right, so let me my ruler out one more time here and connect our lines. And then we want to identify the angles in the fourth quadrant. So as I move from, get back up, right? Sorry, I have sideways to draw. As I get back up from 3 pi over 2 and move to this first quadrant, then remember the angle right here in the first quadrant is 5 pi over 3. And then we move to the multiple of 4, which would be 7 pi over 4. And then we move to the last one here, which will be multiple of pi over 6, and that's going to be 11 pi over 6. So those are my angles at those 3 points. So I want you to list your coordinate point, and then I want you to find your tangent value. So remember, the coordinate point is just the reflection. So you could think about reflecting the point from here to here. You could think about reflecting the point from here over to here. Different ways to think about reflecting that around the circle. So go ahead and pause your video, and I want you to write your coordinates in here, and I want you to write your tangent values here. Pause your video. All right, so hopefully, here's what we have. So we found the coordinate points here and hopefully remembered that because all the points graphed in the fourth quadrant on the Cartesian coordinate system are plus, then a minus, then we're also going to have a plus and a minus coordinate here. So we can reflect these points down straight into the fourth quadrant. Easy, easy. And then when we are doing our tangent values, we're going to be doing, again, sine over cosine, which means that one is positive and one is negative. So that means when I take a positive divided by negative, all my answers in this quadrant for tangent should be negative. So I can reflect my root 3 over 3 down here, and it becomes negative root 3 over 3. I can reflect my 1 down here, it becomes negative 1. I can reflect my root 3 down here, it becomes negative root 3. So I have my tangent values of this, 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 and then we already talked about what happens here at pi over 3. We know it's undefined. What's going to happen when we get back up here to pi over 2 and we're looking at tangent? So here, remember, we said that tangent was equal to 0. We calculated that right there. So let's write it up here where it's easier to see. Well, when we go all the way around, just because we're calculating at 2 pi doesn't change the value because the terminal side is at the exact same spot. So it's still going to be equal to 0. So hopefully you can see that there is definitely some patterns here. We spent the time calculating it in the first quadrant, so you would know how to find the ratios of the tangent because that's what it is. It's just the slope of the terminal side. That's what tangent ratio is. And once you know these values, then you can see like the coordinate points reflect into the different quadrants, like sine and cosine reflect into the different quadrants, also tangent now. We know how to reflect in the quadrants. So once we keep emphasizing making sure you know this. The only thing you have to worry about in tangent then is remember that when you're on this vertical line that the tangent slope is undefined. When you're at the horizontal line, the tangent is 0 because the sine values are all 0. So 0 divided by anything is 0. On the vertical line, the sine values are a number, but the cosine values are 0. So if we're dividing by cosine and cosine happens to be 0, then that would also mean that's when tangent is undefined. So in this case, what's happening here is as the angles progressively move this way, the slopes are steeper and negative in the direction of negative approaching 0. So we can add that to our list. So as we move from theta 3 pi over 2 to theta 2 pi, and we're moving around our circle in this direction, the slopes are negative and they're getting smaller as the terminal ray approaches that 0, which has a slope of 2 pi. So this is kind of giving you a good idea of how those rays are behaving and how we know kind of what those tangents are because we know that this is a ratio which just represents slope. So we're looking at the terminal slopes or the slope of the terminal side of our angles. So the key concepts that we want to make sure is that each time that the terminal ray is vertical, then the slopes are undefined because they're approaching either positive infinity or negative infinity. And then when we graph the tangent function, this means we will see vertical asymptotes at theta equals pi over 2 and theta equals 3 pi over 2 because what is a vertical asymptote? It's when the slope is undefined. So for each half turn around the circle, we're going to create another vertical asymptote. So each half turn is going to create another vertical asymptote. So we're going to have a vertical asymptote here. As we travel to here, we're going to have a vertical asymptote. As we travel back up here, we're going to have a vertical asymptote because remember, unless we restrict it, the circle can go on forever. But every time we do a half turn around the circle, we're going to have undefined slopes. So that's kind of a characteristic that we want to make sure we're thinking about as we move on to the next part. All right, so we're going to kind of put all this together. We've talked about how and what things look like behaving on a circle, but just as we did sine and cosine, we're going to take that circle apart and put it on a coordinate graph. So you're probably going to be flipping back and forth a little bit in your notes so that you can come back and reference the things that we did here. to the rectangular graph, which we're getting ready to talk about. All right, so in this graph, this is what our actual tangent graph looks laid out. So the first thing that we want to make mention of is we already talked about every half turn that you're going to see a vertical asymptote. So this is definitely different from sine and cosine graphs because in sine and cosine graphs, we have nice, smooth, continuous curves that oscillate between a maximum value and a minimum value. And on the parent function, that max and min, when it hasn't had any transformations applied to it, is bouncing between -1 and 1. So the first main difference I want to talk about is that when we're looking at this graph, we have lots of different vertical asymptotes. And what we consider one branch of the tangent function will fall between vertical asymptotes. So what that means is this little wiggle that's happening between -pi/2 and pi/2 is considered one branch. And that's also considered principal branch or the main branch we look at. But then on the other side of pi/2, it comes back down here and it wiggles up again and it reaches the rest of its period over here at this one. And it just keeps doing that wiggle up, bouncing between vertical asymptotes to vertical asymptotes. So this is the graph of the tangent function. So you have that in your notes. And then we're going to talk about some key points here that we want to make. So first then, what is the period of tangent? How long does it take from beginning of the wiggle to the end of the wiggle? In other words, between the two -pi/2 and pi/2. Let's look at this one right here. And this will be like our principal branch that we're going to talk about. So I'm going to go ahead and highlight it here. So we'll talk about that one. So there is multiple branches, but let's get all our characteristics from one. So everybody's talking and looking at the same thing. So how long on our horizontal axis does that occur? It takes from -pi/2 over here to this pi/2 to have one full period. So what is pi/2 plus pi/2? That's going to be a whole. So if you want to think about that, is you're going from pi/2 negative to positive pi/2. Then I'm adding this distance from half to the half. And so that makes it a total period of pi. All right, so half to half. Go back to your circle and you can think about it from here to here is one period, from here to here is one period. And so in this period from pi/2 to 3 pi/2, you can see we have those negative tangent values and we have positive tangent values. And we look at this wiggle graph, we have negative tangent values and we have positive tangent values. So it all kind of ties to the graph itself. All right, the next thing. So this was a period of tangent. So the next thing, since we have many asymptotes, how can we write the equation to represent all vertical asymptotes? And so when I'm saying that, that means I need some equation that represents all vertical asymptotes. So hopping from this one to the next one to an infinite number I could see off the graph that I currently have on this page to an infinite number back this way that I can't see off the page. So as we're doing that, we're going to kind of write, use a little bit of a notation. And we talked a little bit about this earlier in the year, and I said we would come back when we do it here because it makes a little more sense. So if I want to go from here to here, I'm going to have to jump how much from one period to the next period. So if this is pi/2 to another pi/2, I'm going to have to jump pi units to get to the next vertical asymptote. So typically then how we write the equation of that line, any vertical asymptote is an x equals equation. And so if we have an x equals equation, then where is the first asymptote that you see from the vertical axis? It's happening right here at pi/2. So I'm going to write that down as my first asymptote. So if I only were writing one, then that's what it looked like. X is going to equal pi/2, a vertical line at pi/2. But now I want to hop from pi/2 over here to 3 pi/2. So I do that by adding, and the variable that we tend to use is called k, which represents the whole jumps, an integer value. And then how much are we jumping over? Pi. The problem is if k isn't designated as an integer value, then you could like say hop from here to here and whoops, that's not a vertical asymptote. It's a point of inflection, but not a vertical asymptote. Or, what if I went, pi over fours, right? So in order to ensure that when we jump, we're jumping from one vertical asymptote to the next, which is a period away, we have to make sure that's whole number of periods that we jump. So we use this notation and it's called K, and that stands for the constant number of values that we're going to use to jump from vertical asymptote to vertical asymptote. We're going to use this little sideways E that means included in the set. And then we're going to do the top of a Z and we're going to move over and do the bottom of a Z because that's the symbol for integers. So what this whole statement means is I'm going to have vertical equations at pi over 2 and I'm going to jump to the next one whole number of times. So let's say I want to jump 2 asymptotes over, then this would be a 2. So then I would do pi over 2 plus 2 pi, and that would give me the equation of that asymptote that I'm looking for. If I'm going to go 3 jumps over, so 1, 2, 3, and I want to be over here at this value, then I'm going to say x equals pi over 2 plus 3 pi. And so then I could take pi over 2 plus 3 pi, combine that together, and I would get the angle where the vertical line is going to be 3 jumps over. Okay, so this is really important because without this statement, then that means you could be putting in fractions. You could put in partial periods and partial jumps, and you wouldn't get to the next whole number. So what does this mean? This means included in the set of integers. And so remember, we've talked about this. Mathematicians are notorious for having lots and lots of symbols to represent words. They can write symbols instead of words. And when you see that symbol, you have to be able to interpret what that means. So make sure if a question asks for you to give the equation of an asymptote, your equation is going to look something like this unless it's asking for a specific one. And so in which case, then you would do the jump, calculate it, and get the actual angle that x needs to be where the vertical line is that you're talking about. All right, so that is vertical asymptotes and how we look at how they jump around and all that fun stuff. So the next thing we're going to look at from this graph is what would be the midline of the tangent theta. So what's the midline? Can you have a midline in a tangent function? It's not like sine and cosine where it's bouncing around. The answer is yes, you can, because the midline is just the middle of the graph. So if we were looking at the middle of this graph, then we would be looking at the points where we have this right here that are centered around, in this case, the horizontal axis. So those are my midlines. And that's still y equals an equation. So on the parent function graph, that would be 0. We still have vertical asymptotes. I'll use the same abbreviation that I'm sure you used in Algebra 2, but we have VAs right here, and the equation of those vertical asymptotes will depend on which primary or which principal you're jumping to and how many jumps you make, right? So anything you write for this is an equation. Looks like this, x equals. Anything you write from this looks like an equation, y equals. If the graph shifts up or down, just like in sine and cosine, the midline goes with it. So you would need to draw a new midline on your graph if that were the case. So I can say now that I know that my midline is happening on the tangent function at y equals 0. And if the graph translates up or down, the midline translates up or down with it. Okay? So then what is the amplitude of tangent? So amplitude of tangent. Remember that the definition for amplitude is half the distance from the top and the bottom of the graph. So I want you to look at these graphs. If this branch goes on forever, ever this way, and this branch goes on forever, ever this way, and this branch goes on forever, ever this way, and forever this way, and forever and this way, where would the top or bottom of the graph be? Well, hopefully you said I can't get to the top or bottom because they go on indefinitely. So remember that we talked about amplitude is the absolute value of A. And then in sine and cosine, it could be negative. It could be a negative A value if it has been reflected over the vertical axis. And those were two different things. So remember we talked about it looking like this, right? This is the amplitude, and then if it's a reflection, so amplitude, and this would be vertical reflection. In our case now, because we can't get to the top or the bottom of the graph, then we're not going to have an amplitude. We could have an A value that talks about vertical stretching and compressing, but by definition, this is not going to happen on a tangent graph because there is no max or min. So in this one, we're going to say, what is the amplitude? There is none. Please don't use the abbreviation NA. That means not applicable. The fact that we don't have amplitude is very applicable to this question. So it's none because there is no max or minimum number in this tangent graph. Okay, so no max, no min, so there is no tangent on the graph. All right, so let's move to this last piece I want to talk about, and this is describing the concavity on one branch of the tangent function. So if we look at our tangent function, we know that the graph changes concavity when you have a point of inflection or when it's looking from concave up to concave down. So for this particular problem, I can hopefully, by now you're comfortable with that, and you can see that we have this piece of the graph, which is concave down. Then it reaches this point, which remember we talked earlier about calling that an inflection point. And then it's going to look like this. And there, it's concave up. So it changes from being concave down. So I'm going to put CCD here, concave down at the inflection point, then it becomes concave up. So on that one branch, we have both concavities. We have concave down and concave up. And notice that pattern is going to repeat to the next branch as well. This is going to be concave down and this is going to be concave up. And it has that point of inflection that's happening on this branch at pi 0. Okay, so describe the concavity of one branch of the tangent function. So I'm not going to, you have to kind of decide, but I'm just going to say in general, it's going to be, it's going to have both concave up and concave down, and it changes from one to the other. That means it changes from concave down to concave up at the point of inflection on the branch. And remember, there's an infinite number of branches, but this behavior is going to be consistent from branch to branch. Concave down, inflection point, concave up. Concave down, inflection point, concave up. Concave down, inflection point, concave up. So that pattern is repetitive for each branch of the tangent function. So hopefully that helps. We do have one of our summary boxes here for the important characteristics of the tangent function. And so just like all forms of writing it, our tangent function can look like this. Y equals or f of x equals. And then the function itself would be a and tan this time instead of sine or cosine. We will have our b isolated and we'll have our theta that has a c shift left or right. Could have a horizontal dilation, could have a vertical dilation, could reflect over the x-axis, could reflect over the y-axis. or could have a vertical shift of D. So these are all things you know well. We've been talking about most of this all year. And don't forget, if you still need a little more visual help on that, I loaded a reference page um, for you to be able to look at to kind of look some of these translations up if you get stuck. So this is the document that I loaded so you can see. Remember, we talked about we insert whichever trig function we're talking about. We've looked at sine and cosine. Today we're looking for tangent, so you substitute in there. And then it kind of gives you a rundown of all of the transformations that you talked about in Algebra 2. So you have that as a resource if you need it. So let's recap and look at the things that are true about the tangent graph. So we know that we can have vertical dilations for the tangent function. So of the graph y equals theta, so tangent theta, and then it's going to be by a factor of A, because remember when we talk about the negatives on A, we're talking about not the vertical dilation, but the vertical reflection over the x-axis. So those are two separate things. Notice that the period is a little bit different here. So before, when we were doing sine and cosine, we would say the period is 2 pi. So we could say 2 pi equals pi over b. Now, because the period has changed in tangent and the period is pi, then your period here being pi, then you would say whatever your period is equals pi over b. Okay? And then we have a phase shift of c units, and that's our horizontal translation. We have vertical translations, which means that the graph of y equals tangent of theta is going up or down by d units. There is no amplitude because there is no min or max. You can still have an a value. You can still have a negative a value. You just don't have technically what is considered the definition of amplitude, because amplitude is half the distance between the max and the min. And as we just observed, there is no maximum point on the graph. I can never get to the top of this branch. I can never get to the bottom of this branch. Therefore, I can never add those two values together and cut them in half. So these are all the characteristics of tangent that we spent quite a bit of time slowly building up today so that you would understand how all this fit together. So now we're just going to practice taking our knowledge that we have and work through a few examples. Then you can proceed to your daily practice, and we'll, use the unit circles here. So we're going to just take a few minutes and go through this. So example 1, do your first and second read. Concepts that you should have just identified in your first and second read were that the name of the function is h. That's important because if it ever says describe, explain, or justify, you need to specifically name the function you're talking about. Don't use vague pronouns. Don't say it does, the graph does, this does that, the function does this, the equation does that. You need to be specific and name it, so always make note of what the name of the function is. That's just a really good habit to get into. It tells you that we have this equation, so we can see we're dealing with the tangent function. We have some transformations that happen here. We've had a horizontal dilation by a factor of 1/2. We've had a vertical dilation by 4, and we've had a vertical translation up by 5. And then it asks us to find what is the period, the amplitude, and the midline. So going through each piece in and of itself, let's start with period. You could do this in any order. And I'm going to write down steps as we do this. You can probably do some of this in your head, but after all, this is your notes. And so we want to pay attention of things like how we got to what we've got. So we've got these values that are going to deal with helping us find period, amplitude, and midline. All right, so the period for this graph is normally pi, and it tells me that I've been horizontally, so my b value, so pulling from my equation, my b value is 2. So then I'm going to say pi divided by 2, which gives me my period of 2 pi. So the period is 2 pi. I'm sorry, not 2 pi, pi over 2, excuse me. So it's really just using this conversion fact. So because I knew the original period was pi, and then I could say pi over, and I knew my b value was 2, so I can know that I'm going to make that conversion. So the whole period is pi over 2. So I'm going to cut my period of pi in half, basically. All right, then the next thing we're going to find is the amplitude. And that should be the easy one because you should say that there is none, no amplitude, because there is no top or bottom of the graph to get to. Now we could find an A value, and we could say that we needed to find the A value. And in that case, then we're looking at this value right here, and we can say A equals 4. But once again, that's not the amplitude because the amplitude is half the distance between the top and the bottom, so that you can go from the midline to the top. You can count the same distance from the midline to the bottom. And since we don't have those values that make us have a top or bottom to the graph, we have no amplitude. So this is real important, and make sure you're making a mental note of this. So there is no amplitude, but there is an A value. Okay, so make sure you can keep those two straight. And then the last thing they asked us is a midline. So if we're doing a midline, then where am I looking on my graph? How do I find a midline? I look at my D value. So since I say know that D is 5 from the equation right here, then I know my midline is Y equals 5. And it has, excuse me, it has to be in the form of an equation. So all midlines are in the form of an equation. All right, good job. So now let's move on to question 2. So as we do a question 2, we do our first and second read. What are the things that we're paying attention to? Well, we're paying attention to the fact that we know the name, that's graph of f. It's a portion of a function, and they're telling us it has to do with sine right here. And where a, b, and c are constants, so that means they're numbers. We want to find the values of a, b, and d, and we want to have supporting work to get us there. So we've made note of information off our graph. We've made note of information here on our second read. So go ahead and pause your video, work it out, do your third read. Don't forget about that third read. The third read is, here are my answers. Did they answer the question to begin with? For instance, if you have a question and you say yes, and the question said find 3, and you're saying, yeah, 3 works, well, that's still not answering the question. So we want to make a point of doing that third read. I know sometimes I don't always do that with you because we're moving through and comparing as we talk, but that is an important skill. So first read, orient yourself to the problem. Second read, annotate, mark up the problem, dig in, College Board calls entering at the problem, make sure you know the names of the functions, what it's asking you to do, what are the givens, what is it you're trying to find. Then you work the problem and do your third read, making sure your answers answer the question. So go ahead and pause your video and work out example 2. Okay, how did you do on example 3? You might have had a little trouble with A, so I want to go back and talk about that unit circle one more time and look at a couple important points on this first primary branch. So we talked about its concave down, and then at the reflection point, which is at 0, 0, then it's concave up. So if you think about your quadrantal angles, then if I want to go between pi over 2 and pi, if I'm halfway between, then I'm at the value 1. And so if I'm going in the negative rotation around the circle, if I'm halfway between 0 and negative pi, then I'm going down to negative 1. So you can look at those values on the circle that we created at the beginning too, right? So if we're going from here and we're halfway up to getting to pi over 2, then at this coordinate point, we know it's root 2 over 2, and we know that that tangent line is 1. So oftentimes, because if we only use quadrantal angles when we're graphing or looking at tangent, then we really only have one point that is viable unless I'm going to calculate some of these more complicated values, because we're going from a half turn, right? So we get up to here, we're having an undefined value. And then we get back down here, we have another undefined value. So we tend to use these pi over 4 angles that fall in between here. So we have some other viable points. So as we use our unit circle values at pi over 4, the value here is 1. The tangent value is 1. So at the angle pi over 4, the tangent value is 1. At the angle negative pi over 4, the tangent value is negative 1. And so we kind of use these 3 principal points here to kind of get our graph shape, and we know it goes from vertical asymptote through this point, curves through this point, curves through this point, and continues out indefinitely getting closer and closer to this vertical asymptote, but by definition of vertical asymptote, it never actually gets there. So thinking about that might help just a little bit on this one, because if I look at my graph here, it goes to pi over 4. Halfway between pi over 4 would be pi over 8. And on this graph, I could look up there and get a 1. Now, if you couldn't tell for sure, then hopefully this would be like a problem where you had an equation, and maybe you had to plug in the pi over 8 into an equation and work it out to be able to get to that answer. But it is just a coordinate point. So what I was trying to see is then how far up does it go to get that point of 1? Or from the halfway point to this point on the graph. And I can see it's a nice intersection at 1, just like on the parent function, when I'm halfway between the 0 and the vertical asymptote at this pi over 4, when I do a vertical move up to the point, I'm at the nice line of 1. So if you can go halfway and up to 1, then you know that it hasn't had any vertical stretches or things like that. So the midline here was happening on the axis. So y equals 0 means that d equals 0. The period then is going from negative pi over 4 to pi over 4. So that's a period of pi over 2. And we said we can take the period equals pi over b. So pi over 2 equals pi over b. And now I know that my b value is 2. So if that's happening here, and then I can find A by figuring out where is that halfway point. And my halfway point between 0 and pi over 4 would be pi over 8. And it goes up to 1. So I can look at the graph in this case. I could actually put in my A's and my B's into an equation if I wanted to. And I could do something like this. 5 pi over 8 equals a tangent. And then inside here, I would have 2 times pi over 8. And then I could calculate that because that's pi over 4. So I could do f at pi over 8 equals a tan pi over 4. And we all know what pi over 4 is. Pi over 4 is 1. So a times 1 is just going to give me that 1. So this is if you had to do so because you couldn't tell a nice point on the graph, that we can tell a nice point on this graph. So this kind of process wasn't necessarily needed, but you have it in your notes if you ever get to an equation where you need to do something like that to answer the question. All right, so go ahead and do your first and second read on example 3. Pause your video. Okay, so we identified the name of the function, which is g, that we have this equation that we can use. It asks us which of the following could be vertical asymptotes to the graph of g, and a reminder about the notation kes. K belongs to the set of integers. Remember, whole number shifts for z. So go ahead and pause your video, answer the question, and we'll come back and compare. Okay, so I went ahead and rewrote the equation and kind of rewrote that in a form I was familiar with. X over 3 is the same thing as 1/3 x. Then I decided to find my period. So I know that the period equals pi divided by b, and my b is 1/3. So that means I am taking pi and multiplying by the reciprocal. So my period is 3 pi. And then I need to find my first vertical asymptote. So I know in the original function, the first vertical asymptote is pi over 2, but the period has changed. So I multiplied by 3. That gave me 3 pi over 2, which makes this now my first vertical asymptote. So all of them said k is an integer, which remember just is the notation we used a minute ago where we did this. Okay, that's the same thing. And all of them said that, so I didn't have to worry about that. The things that were different on them definitely were that first vertical asymptote. So since I knew my first vertical asymptote is supposed to be at 3 pi over 2, that ruled out this one, and this one, leaving me as C being my correct choice. All right, moving on to example 4. Go ahead, do your first and second read, and pause your video. Okay, so we know that the name of the graph is graph of M. We know that we have a portion graphed. It says, mine says above. If yours says above, make note it's to the left. Which of the following could be the expression for M? So you're going to go ahead and pause your video. Think about what you know about midlines, periods, finding A, finding vertical asymptotes, and figure out which of these will match the graph that you're currently looking at. Pause your video. All right, let's see how you did. So for me, I noticed that you can see where the midlines have dropped down. So you can see that the wiggle, that point of inflection is happening down here on this horizontal line at y equals -2. I went over one from the midline and up, and it looked like that vertical distance was one going both ways. So I'd know that there wasn't any kind of stretch. And I really didn't need to do that because none of my answer choices have that, but that might be something that you initially thought of. So the next thing I needed to deal with was the period, because if I know the period, then I'll know if it's had any horizontal dilations. And so my period goes from negative pi to pi. So that means if it's going from negative pi to pi, I have a period of 2 pi. And we know our conversion is 2 pi equals pi over b. So I can solve for b and find that that's 1/2. So with these two pieces, I can rule out all of my choices that don't apply. So d is -2. So that rules out both of these choices. And then b was 1/2. So remember, the other way to write x over 2 is 1/2 x, like we did right here in the problem above. And so then it could only possibly be this one and this one. So that rules out this choice. And between those two, the only one that has the -2 for D and the B at 1/2 is choice A. All right, last problem, guys, example 5. So we are going to take the space here, and on your note sheet, right above example 5 to the right-hand side of the question that we just did, so you should have some space over here on your note sheet. I want you to draw the first quadrant of your graph. So draw your quadrantal angles. So what I mean by that is we're going to do this, and we're going to do this. And then we are going to label all of the sine, cosine, and tangent values in the first quadrant and the quadrantal angle markers. So we're going to have 0, -1. So like here, we could do the coordinate point 1, 0, and that's going to do your cosine and sine, right? So then you'll add tangent to that. So we're going to have this up here, and that's going to be pi over 2, and we know that that one is going to be 0, and then up 1. Here we have 2, I'm sorry, 0 and 2 pi. Here we're at 3 pi over 2. Over here we're at pi, and we know that coordinate is -1, 0. So we're going to lay in the three angles in our first quadrant that we talked about being on our quadrantal angle. We're going to write down the coordinates, so that's showing our sine and cosine values, and then we're going to write down our tangent values that go with all of these angles. So go ahead and create your first quadrant. Make sure that you're keeping track. So let me do a little graph here, and then from the center about halfway, and then on this side of the halfway, we have that other point here. So we're looking at these angles. Put in your radian measure, coordinates, cosine, sine, and tangent values. Pause your video. All right, how did you do? So we had the cosine, the sine, and the tangent, 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 and cosine, sine, and tangent up here. And we made a mental note that remember when we're on the horizontal line, the tangents are 0, and when we're on the vertical line, because the vertical line has an undefined slope, tangent is undefined at these two places. All right, pause your video one last time, and I want you to use your first quadrant unit circle to answer the following questions. Remember that if the angle is positive, you're opening in the counterclockwise direction. If the angle is negative, you're opening in the negative direction, so the clockwise direction. And remember that all you have to do to figure out where this is, if you know where it is in the positive direction, like I know this is +4, and from the +0 axis, it's in the first quadrant. And if I want to find it down here, I go to the 0 axis and I just go in the first quadrant in this direction. It's not a matter of having to memorize all your negative angles. It's a matter of understanding where they are in the positive rotation and then just reversing it. So instead of going from here to here, then you're going to go in the negative direction from here to here, the same distance. All right, pause your video one last time. Answer these questions based on your unit circle. Hopefully it doesn't need a whole lot of calculating. And we will check in one last time to make sure we're good to go. Pause your video. All right, so unit circle values. So these are things that we shouldn't need to have to do much calculation from now. And we did write that first quadrant up above. So we had all the information we should need, and we should know how to reflect points into quadrant 2, quadrant 3, and quadrant 4 to be able to determine sine, cosine, and tangent angles. All right, let's see how you did. So I went ahead and wrote down what quadrant it was in, so you could kind of have that in your notes. But A, if you did the ratio and you did sine over cosine of your pi over 6 angle, then you would have got 1 over 3. And remember that we need to rationalize that. So we would do root 3 times root 3, which means 1 times root 3 is root 3. Root 3 times root 3 is root 9, which is 3. So this is our final answer. And that was a quadrant 1 angle. On B, we're going in the negative direction. So I look up here and I said, okay, 4 is right here. So now I'm going to go that same distance in the negative direction. So I drew a picture of where that angle would be. And so I know that tangent and pi over 4 coordinates are root 2 over 2, root 2 over 2. Anything divided by itself is 1. And because it's in the fourth quadrant, tangent is negative. So the answer is negative 1. On C, we're in quadrant 1, so we know that quadrant 1 at pi over 3 is going to have the coordinates 1/2 root 3 over 2, so you can divide sine over cosine, and it should give you root 3. In D, 5 pi over 6 falls in quadrant 2. So I know that the tangent value of 5 pi over 6 is a multiple of pi over 6. So if I know that my tangent value for pi over 6 is root 3 over 3, then this multiple is also going to be root 3 over 3. This multiple angle is going to be root 3 over 3. And then I just adjust the value based on what quadrant it's in. So I know in quadrant 2, I have one value that's negative, one value that's positive. So my answer is always going to be negative for that tangent in quadrant 2. All right, so now we're looking at E, negative 4 pi over 3. So I know that 4 pi over 3 is going to fall in the third quadrant. So if I reverse that, now it's going to be in the first quadrant. So the angle from here all the way and terminates here is negative 4 pi over 3. The angle from here to here is positive pi over 3. So negative 4 pi over 3 is a multiple of pi over 3. And we know that pi over 3 has a tangent value of root 3. Know that this is putting me back in quadrant 1 where the tangent value would be positive, then the tangent value of pi over 3 is going to be the same ratio as the tangent value of negative 4 pi over 3. All right, so let's move into this one. We're doing 7 pi over 4. It's in quadrant 4, and we know that the tan values in quadrant 4 are negative. We know that any multiple of 4, pi over 4, has the coordinates root 2 over 2, root 2 over 2, so anything divided by itself is 1, and because it's in the fourth quadrant, I know it's a negative 1. All right, let's look at G. So G is a quadrantal angle. So then we either have with tangent, we have values that are 0 or we have values that are undefined. And the values that are undefined are the vertical asymptote, not vertical asymptote, excuse me, vertical axis, because we're going vertically and that means it has a slope that's undefined. At pi, we are talking about another quadrantal angle, but that's on the horizontal axis, and all slopes in the horizontal axis will be 0. And then on I, the last one here, it is pi over 2, which is on the vertical axis. So that's a quadrantal angle, and all vertical lines have a slope that's undefined, so it's undefined. Please get in the habit of using like the abbreviation UND for undefined. I don't want to see NA on your paper. I want you to be more exacting than that. Because the fact that this is undefined is very applicable to this particular math problem. All right, that wraps it up. I know this was kind of a long lesson, but I wanted to go a little bit slow and make sure you were really understanding all the ins and outs of the tangent function. So we will come back. We will do more on the next lesson with tangents and how those tie into sine, cosine, and we'll be looking at some concepts of inverses next time as well. All right, thanks so much, guys. Bye.